for our 25th Vodcast for fluid dynamics. We're almost done. This is the second to last Vodcast. And today we are covering sections 9.1.1 and 9.1.2. The topic of this chapter is external flow, which means if you have a body that is completely immersed in a fluid, the fluid moving over that body. So that could be a plate submerged in a swimming pool, or it could be the wing of an aircraft. It could be the entire aircraft, wings, fuselage, and so forth. But we may be looking at the characteristics of the airfoil or the wing in being submerged in air. And we're going to look at some characteristics of what the fluid looks like around the boundary of that object. And we're going to talk about some concepts called lift and drag, which is actually how an airplane flies, among other things. But also has a lot to do with when you design wind turbines. You have to take those factors into account as well in order to generate electricity instead of not generating electricity. So having said that, we're going to go over here to the document cam and take a look at these ideas of lift and drag when we talk about flow going over a body. So in your textbook, one of the things that your authors do that I think is very good is they talk about the fact that streamlining is something that reduces the idea of drag. And drag is just like it sounds. Drag is a force that creates a frictional delay, or in other words, drag, which is shown by this scrolly V, is a force resulting in a delay or resistance to movement. And lift is also a force, but this is due to a pressure differential and also to work. Which causes or allows an object to, in the case of an airfoil, become airborne. All right. So if we take a look at a typical airplane wing, for example, airplane wings tend to have a shape that looks something like this. And they are often explained using the Bernoulli principle, but this is workable but not complete. There's another factor that goes on that if you get into aerodynamic design, you'll discuss the idea of the work done by the wing actually pushing air down. But basically what we have is a leading edge of the wing. And although this is not completely accurate, the model is that the air will hit the leading edge and then it will separate around the wing and then come back together somewhere behind the wing. So that if this length, the path that the air has to take above, this I don't mean lift, I mean length up above, and the length below, if the length above is less than or is greater than the length below, what that does is creates a lower pressure on the top than on the bottom. And as I said, this is actually, if you think about every action having an equal and opposite reaction, this is also pushing air down, and the pushing of air down pushes air back up. But in any case, whatever creates this differential between the bottom and the top allows the wing to be lifted upward, and that is the force of lift. Now drag, on the other hand, is found when this air has viscous forces, and there's a viscous effect around the wing, and what ends up happening is that this viscous, this air passing here creates a shearing stress along the edge of the wing that acts as a frictional retardant to motion. So in flight, for example, there are 4 forces that are balanced. This would be in level flight. You have lift, balancing gravity or weight, and you have something moving the airplane forward, which is called thrust. That's what the engines are all about. Balancing, drag. All right, and so this is level, non-accelerated flight. So it looks relatively simple, but it certainly makes a big difference in modern living. The way that this allows us to achieve to achieve the miracle of flight. Now, lighter than aircrafts like dirigibles act in a little bit different manner, don't they? Because we already learned when we talked about buoyancy, if you have a dirigible like the Hindenburg helium or hydrogen balloon, that the density of the material in here is less than the density of the surrounding air, and so the displacement of the air by this large balloon of helium or hydrogen causes it to lift in a different manner. So this is a dynamic lift and this is a passive lift. But anyway, so these are some of the ideas that we talk about when we are talking about external flows and talking about the idea of air or fluid of any sort moving past an object. So in that's kind of what we talk about in section 9.1.1. They talk about the fact that the force of drag, so this might be in pounds or newtons, and the force of lift, also in pounds or newtons, is relative. These are very difficult to measure because they are functions of variables that are difficult to obtain in real world conditions. So we revert to the method of dimensionless modeling, and we develop 2 dimensionless coefficients that will help us describe these properties of lift and drag. And one of them is called the lift coefficient, C sub L. And it is lift force divided by 1/2 times the rho of the fluid times the velocity squared of the fluid times the area. Now this area is called the characteristic area, and it's usually the projection of the front of that object if you were looking straight down it. So in other words, if you have, my airplane wing's too messy, I'll draw another one. If you have an airplane wing that looks like this, and the wind is looking at it like this, all right, if I were to turn this 90 degrees, I might see the wing looking something like this. So in other words, I'm standing in the path of the air, looking at the edge of the wing or the leading edge of the wing, and this is more or less the area that I see. Sometimes it can be the area of the top or the area of the bottom. It can have different meanings in different flow regimes, but at this point of the game, if you just think about it as being a characteristic area related to the flow of the fluid, that will be sufficient to take care of all the problems that you need to solve now, and give you some food for thought for later on. All right, similarly, C sub D, which is the drag coefficient, is equal to the drag force divided by the same term, 1/2 rho u squared A. Okay. Now, if you look at these, just examine these coordinates for dimensionality. You can see drag is in units of force. Half is just a constant. Density is in mass per length to the third, because it's mass per volume. U is length per time, so length u squared is length squared per time squared. And area is length squared. So you can see that length to the fourth here cancels length third here, and you're left with mass length per time squared in the denominator. And we know force is equal to mass times acceleration, so it's equal to mass length per time squared. So we can substitute those units in, and looky there, we are dimensionless. All right. Now, it turns out that when we talk about the characteristics of flow past an object, Reynolds number is extremely important, sort of governs the nature of the flow. And the other variable, or the other dimensionless parameter that is extremely important, is the Mach number. In other words, are we traveling at a speed that is above, at, or below the speed of sound? And that has a great deal to do with the nature of the compressibility of the fluid. But we're talking about subsonic flow pretty exclusively here. And so the Reynolds number is what we're going to talk about when we talk about the boundary effects of the fluid and what happens around the immersed object. So first of all, we know from our previous work in other chapters that the Reynolds number can be described as density times U times some characteristic length over mu, viscosity, or we can remember that rho over mu is equal to nu, which is the kinematic viscosity. So we can simplify that equation just a little bit. And we can say velocity times characteristic length over kinematic viscosity is an expression for the Reynolds number. And Mach number is just equal to the speed over the speed of sound. Not the speed of light, I wish to mention, but the speed of sound. Another variable that we look at quite often is the Froude number, which is speed divided by the root of gravity times length. All right, and so the most important thing when we talk about immersed flows at subsonic velocities is the Reynolds number. So in your textbook on page 540 and 541, they discuss this in fairly good detail. And it says basically the gist of this whole idea is that the characteristic of flow past an object is dependent upon the value of the Reynolds number. And as usual, it's hard to quantify exact numbers, but we talk about low Reynolds numbers, which would be very, very laminar flow. And what happens there is that viscosity of the fluid is very important. All right. Then we have sort of intermediate numbers. So let's say this is maybe like 0.01. It's really, really laminar. It's really, really slow fluid movement for the most part. Then we have sort of intermediate Reynolds numbers, maybe not intermediate in the sense of laminar to turbulent, but just sort of in the middle of this group, and not mathematically in the middle, just some number in the middle, where viscosity is important, but it's not as important. It's important for less area around the object. Has a smaller area of importance. Let's do that. And then if we have extremely high Reynolds numbers, say in the order of 10 to the 7th, we have a very small area where viscosity is important. Okay. And basically the area, if you recall, the area where viscosity is important, the viscous region, is referred to as the boundary layer. Okay? And that's really where there's sort of a system between whatever object we have being submersed in this fluid. We have the velocity profile of the fluid moving toward our object. And for a low Reynolds number, we're going to have a very, very large area where the viscosity of that fluid is extremely important. And we find that the streamlines of these fluids are deflected a long way away from the object that is in the flow regime. And that can be tested in a wind tunnel or through dye studies, and we can take a look at those in a lot of different ways. Now, so this is very low Reynolds numbers. When we get into intermediate Reynolds number, we might have this object, same kind of a flow profile, but if it's the same fluid, if you look at this, if it's the same fluid and the same object, it's probably going to be moving faster, because you would probably be the variable that's changing in that case. We'll see that the boundary layer is much more smooth, and we can also see, when I say smooth, I don't necessarily mean, I mean it's smaller. The nose, if it's a parabola or a nose, the nose is narrower and the boundary layer remains closer to the object. So there is still deflection of the streamlines, but there is less deflection at those intermediate Reynolds numbers. All right, and then when we get into very high Reynolds numbers, like I said, at the order of 10 to the 7th, you have a situation where the fluid is moving toward the object. The Reynolds number is quite high, of a magnitude of maybe 10 to the 7, and you'll see that the boundary layer just really is just in the immediate surrounding area to the object, and there's almost no deflection of the streamlines. Right. Now, in any object like this, whether it's just a rectangular bar or an airplane, the area behind the object, downwind, is going to be deflected considerably. Like here, for example, it's going to be very, very low. And the area where the deflection occurs is referred to as the wake. So you'll have, and there are some effects that have been noted. For example, if you have a large airplane taking off, and they have to take off at very high speeds in order to generate enough, they have to have enough thrust to go very fast to get a big enough effect so that they will attain lift. And if you look at if you looked at an airplane from behind, you'll notice they have extremely large wings relative to the size of the fuselage. And when this occurs, you'll have a wake that especially comes off on the end of the wingtip, where the wind will be really eddied up, and there will be a lot of pressure problems and pressure differentials, unpredictable pressure regimes going on in the wake of the aircraft. And those are actually referred to as wingtip vortices. And they can be very dangerous if a pilot of a small aircraft takes off immediately behind a large aircraft. So the solution for that is just to wait 10 or 15 seconds in order for those pressure differentials to dissipate. All right, so having sort of gone through the ideas of lift and drag, boundary region, and wake, let's take a look at a problem or two. We'll do problem 9.2 and 9.9 to sort of see how these ideas are used in our homework set. All right, so if you go to your textbook and find problem 9.2, this is on page 609 of your textbook. So I'll read through the problem, redraw the figure, and work it out. All right, so it says 9.2 says that a fluid flows past a two-dimensional bar. So the bar looks like this, and this would be the leading edge, and we have a velocity of u, capital U, and we're told that the width of the bar is b. So we're just using some variable b, and we are given this dimension as being 10h. So in other words, it goes b back into the page, and it's 10h long. We're told that the pressure on the leading edge is 1/2 rho u squared. So it looks rather familiar. That we have some sort of a tau average on the top, some sort of a tau average on the bottom, and that we have pressure. Oh, also this has a height of h. We have a pressure on the back end of 0.2 times that same quantity. All right. So the question is, the pressure on the ends of the bars are shown, and the average shearing stress on the top and bottom are T average. Assuming that the drag due to pressure is equal to the drag due to viscous effects, all right, so that tells me the viscous effects are friction, right? So the drag of friction is equal to the drag due to pressure. We don't know what those formulas look like yet, but we will in a moment here. But assuming that they are equal, we want to determine tau average in terms of dynamic pressure. Some function of dynamic pressure, which is 1/2 rho u squared. All right, and we also want to determine the drag coefficient, which is C sub d. Okay, so this is part A, and this is part B. All right, so first of all, if there's a good example in your textbook, example 1.1 in this chapter on page 537, we know that tau, which is shear stress, is equal to some sort of a force over an area. And so if we multiply through by A, the tau times area is equal to a force. We also know that drag, because drag is a force, is going to equal some sort of an integral of tau dA. And if we have tau on the bottom and tau on the top, and we're told that they are the same, then drag on the top plus the drag on the bottom would equal to, each one of them is equal to this, so it's equal to 2 times the integral of tau dA. All right, and if tau were constant, we could pull it outside. It's probably not, but we can approximate this integral by saying 2 times tau average times the affected area. All right, so continuing with this idea, let's say d sub f, which is friction drag, is then going to be equal to 2 times tau average times the area. And what is the area? Well, it's 10 times h times b, which is the width. So 10 times h times b, which is just that leading edge area. So I can say then it's equal to 20 tau average times h times b. And if I take a look at pressure drag, which I know is different on the leading edge as on the trailing edge, but if I think about the force, going back to the same idea, that force per area is equal to a pressure, okay? It can be a pressure or it could be a tau. So the force is equal to pressure times area, and if I'm talking about the force, the drag force due to pressure, then that would be equal to whatever that value of the pressure is times the area. All right, so we want to have this as a function of dynamic pressure. So if we take the leading edge times the area, subtract the trailing edge times that pressure, then we should have an expression for the difference in the pressure from one edge to the other. So we have, well, actually a force, because if I multiply it by area, I'm talking about the force. So the force on the leading edge would be this times the area, which is, now this time we're going to have a b times an h, because we're talking about the area that's being b, this is h, and b goes back into the board. So this is just b times h. It's not along the side, the friction drag is a b times the 10h, but here we're just looking at that straight on leading edge. So if we have 1/2 rho u squared times bh, that's on the leading edge. Subtract from that what's going on the trailing edge, minus 0.2 times 1/2 times rho u squared, once again times the bh. And I can simplify that. First of all, minus minus is a plus. All of the terms are the same. Here we have 1. Here we have 0.2, so that's 1 plus 0.2 is 1.2. Then we have the dynamic pressure. And then we have the area of that leading edge. All right, so now we have an expression for d sub p, and we also have an expression for d sub f. We're told that d sub f equals d sub p, so we can set those two equal to each other. And you know, it would be very easy to just, instead of calling this 1.2 times 1.5 or 1/2, I just was leaving it in that form because this is the dynamic pressure, including that 1/2. Let's go ahead and just set it equal to 0.6 rho u squared bh. All right, so if they're equal, then we can set those two equal to each other. So far so good, yes? And then we can just solve for tau average. Equals this term. I'm just going to divide through by 20 HB. H is canceled, B is cancels. We have 0.6 divided by 20. And then we have P, or rho u squared. But I still want to express that in terms of the 1/2 rho u squared, because it asks me to express it in terms of dynamic pressure. So what I'd like to do is to leave my 2 down here so I can have that 1/2. And then what that's going to leave me is 0.6 divided by 10, which is 0.06 times rho u squared. All right, so to rewrite this in terms of dynamic pressure, it's 0.06 times 1/2 rho u squared. All right, and so that is the answer to part A, which is the tau average. So we should tau average in terms of dynamic pressure. So tau average is 0.06 or 6% of the dynamic pressure. All right, the second problem, or the second part asks us to find the drag coefficient. All right, well, first of all, we have to get our total drag force, which is going to be d sub f, drag due to friction, plus drag due to pressure. So, and both of those things added together is going to be the equation from page 539 for the drag, for the force of drag, or based on the drag coefficient. So we start with this equation, C sub d equals drag force divided by dynamic pressure times area, and we solve that for drag. So we can say C sub d times 1/2 rho u squared a equals d. All right, so this equals 1/2 rho u squared a. So we have our total drag is equal to something in terms of this. Oh, that's my drag coefficient, my area, there we go. So I can say then drag is equal to C sub d times 1/2 rho u squared times the area, which is just going to be the BH. Well, I should add both of those together instead of doing it this simply. Let's go ahead and just take d sub f and rewrite that. We know that that is 20 HB tau average, and we know that d sub p is 1.2 times 1/2 rho u squared times BH. So there's my d sub p plus d sub f. All right, so I have that. And then we know that's equal to C sub d times 1/2 rho u squared times BH, because that's the area. All right. Anyway, and I'm running out of time. There's going to be a class coming in here. So I was just looking at simplifying that. Knock out all of your variables, and you come up with the fact that C sub d then is equal to a dimensionless value of 2.4. All right, and that is it for problem 9.2. You can work through that math. You'll see that all the arithmetic comes out correctly. If we take a look at 9.9, if I have time, I think I do. Problem 9.9 in your textbook says approximately how fast can the wind blow past, so we're looking for U, a 0.25 inch diameter twig if viscous effects are to be of importance throughout the entire flow. So my RE is less than 1, really. I could even say 0.1, but we'll leave it at 1. Repeat for a 0.004 inch diameter hair. All right, so let's do this. We know if RE is